Chapter 25. Long-term structural maintenance. Long-term stability depends on whether structural conditions are preserved as membranes turn over and environments change. Every cell continuously replaces lipid components through remodeling cycles that respond to substrate availability, oxidative exposure, and metabolic demand. Without control over these inputs, newly built membranes drift away from the properties required for stable signaling and transport. Maintenance is therefore an ongoing process that governs what materials are available for reconstruction, how damage is handled, and whether the system replaces degraded structures with components that restore or further degrade function. Membrane turnover operates through selective replacement rather than wholesale rebuilding. Individual phospholipids are removed, modified, and reinserted based on the fatty acid pool available at that moment. This means that the composition of circulating and stored lipids directly determines future membrane properties. When stable substrates dominate, replacement cycles gradually reinforce structural integrity. When unstable or oxidized lipids are present, they are incorporated into membranes, introducing variability in packing and increasing susceptibility to further damage. Control of the substrate pool defines the direction of this process. Oxidative load determines the rate at which structures degrade. Reactive species interact with unsaturated bonds, altering lipid shape and disrupting membrane organization. This increases permeability and destabilizes embedded proteins, forcing higher turnover to maintain function. When oxidative exposure exceeds the system's capacity to repair or replace, damage accumulates faster than it can be resolved. Reducing this load slows degradation, allowing maintenance processes to operate without constant deficit. Repair systems act on damaged lipids and associated structures to restore function. Enzymatic pathways identify altered components, remove them, and reassemble membranes using available substrates. The effectiveness of these systems depends on both energy availability and the quality of replacement materials. Adequate ADP supports the removal and rebuilding processes, while a stable lipid pool ensures that repaired structures return to a functional state rather than repeating the cycle of instability. Energy production must remain consistent to sustain maintenance. Remodeling, transport, and repair all require ADP. When mitochondrial efficiency is compromised, energy becomes limited and maintenance processes are deprioritized. This allows structural degradation to progress, further impairing energy production and creating a reinforcing cycle. Restoring mitochondrial membrane integrity supports the energy supply required to maintain overall structure. Transport systems influence maintenance by controlling how lipids are distributed and delivered to tissues. Lipoproteins carry triglycerides and phospholipids through circulation, directing them to areas of need. When transport operates efficiently, tissues receive substrates in proportion to demand, supporting uniform maintenance across the system. Disruption in transport leads to uneven distribution, where some tissues rebuild while others degrade. Hormonal and neural regulation coordinate maintenance activities across tissues. Signals that reflect energy status, nutrient availability, and stress conditions adjust the rate of remodeling and repair. When these signals are interpreted consistently, maintenance processes scale appropriately. Variability in signaling leads to uneven maintenance, reinforcing fragmentation. Time becomes a defining factor in structural preservation. Membrane replacement occurs over weeks to months, depending on tissue type. Short-term changes in input do not immediately translate into structural change, but sustained conditions alter composition progressively. Consistent input of stable substrates allows gradual replacement of unstable components, while continued exposure to damaging conditions prevents convergence toward stability. Maintenance also requires limiting repeated disruption. Continuous introduction of unstable lipids or persistent oxidative stress forces the system to operate in a reactive state, preventing completion of repair cycles. Removing these inputs allows maintenance to proceed without interruption, enabling the system to reach a steady structural state. Long-term structural maintenance therefore depends on controlling the inputs that define membrane composition, reducing the forces that drive degradation, and sustaining the energy and signaling conditions required for repair. As these factors align, remodeling cycles reinforce stability rather than erode it, allowing membranes across tissues to maintain consistent properties over time and supporting reliable system-wide function. Continuous lipid turnover and replacement. Membranes are not static assemblies. Every cell operates a continuous cycle of lipid removal, modification, and reinsertion that reshapes membrane composition over time. This turnover does not occur as a single event, but as a distributed process across enzymatic pathways that selectively edit individual phospholipids. Fatty acids are cleaved, exchanged, and reesterified based on the pool of available substrates, meaning that the circulating and stored lipid environment directly determines what membranes become in the future. Structure is therefore not fixed. It is rewritten continuously through these replacement cycles. The Land cycle governs much of this remodeling. Phospholipids remove fatty acids from existing phospholipids, creating lysophospholipids that are then reacylated with new fatty acids supplied by the cellular pool. This process allows membranes to adapt to changing conditions, but it also makes them vulnerable to the quality of incoming substrates. If stable fatty acids dominate, each cycle reinforces membrane packing and reduces variability. If unstable or oxidized fatty acids are present, they are incorporated into the bilayer, introducing irregular geometry and increasing susceptibility to further damage. Turnover rates vary across tissues, but remain constant enough to ensure that membrane composition reflects long-term inputs rather than short-term fluctuations. Rapidly active tissues, such as the liver, remodel more quickly, while others change more slowly, but all participate in ongoing replacement. This creates a temporal layer where past inputs persist within structure, gradually displaced as new lipids are incorporated. The system therefore carries a memory of previous conditions until sufficient cycles replace those components. Oxidative modification accelerates turnover by marking lipids for removal. Reactive species alter double bonds and disrupt membrane organization, triggering enzymatic recognition and extraction. This increases the demand for replacement and shifts the system toward higher throughput. If replacement materials are stable, this process can improve membrane integrity over time. If they are not, turnover becomes a loop where damaged structures are replaced with equally unstable components, preventing convergence toward stability. Transport systems determine how replacement materials are delivered. Lipoproteins distribute triglycerides, phospholipids, and cholesterol between tissues, directing substrates toward areas of demand. The composition of these carriers reflects dietary input and endogenous synthesis, meaning that systemic lipid distribution shapes local membrane remodeling. Efficient transport allows uniform replacement across tissues, while imbalances create regions where turnover leads to different structural outcomes. Energy availability constrains the entire process. Lipid remodeling requires ADP for activation, transport, and enzymatic function. When energy supply is consistent, turnover proceeds without interruption, allowing gradual convergence towards stable structure. When energy is limited, incomplete remodeling leads to accumulation of partially processed lipids and inconsistent membrane composition. Over time, repeated cycles of removal and replacement determine the steady-state composition of membranes. This state is not achieved instantly, but emerges from the cumulative effect of thousands of small changes. Each cycle shifts the balance slightly, and sustained conditions drive the system toward a new equilibrium. Stability, therefore, depends on maintaining inputs that consistently bias these cycles towards structural integrity. Continuous lipid turnover and replacement define how membranes evolve. By controlling the substrate pool, limiting oxidative disruption, and maintaining energy supply, these cycles can be directed toward building stable, uniform structures. Without that control, the same mechanisms produce variability and instability, embedding those properties into the architecture of the system. Environmental pressures and adaptation. The body does not operate in a fixed environment. Temperature, nutrient availability, light exposure, toxins, and mechanical stress continuously shift the conditions under which cells must maintain structure. Adaptation is the process by which membranes and their associated systems adjust to these pressures without losing functional stability. This adjustment is not abstract. It occurs through changes in lipid composition, protein behavior, and transport dynamics that allow the system to preserve containment, signaling precision and energy production under altered conditions. Temperature imposes direct constraints on membrane behavior. Increased temperature accelerates molecular motion, reducing packing density and increasing permeability. Lower temperature produces the opposite effect, tightening packing and restricting movement. Membranes adapt by altering lipid composition to maintain a usable range of fluidity. Saturated lipids resist excessive fluidity under heat, while unsaturated lipids prevent rigidity, under cold conditions. Cholesterol acts as a local regulator, inserting between phospholipids to limit extremes in either direction. This balancing process allows membranes to maintain consistent transport and signaling despite external variation. Nutrient availability shapes the substrate pool used for continuous remodeling. When stable lipid substrates are available, adaptation reinforces structural integrity while adjusting to demand. When unstable or oxidized substrates dominate, adaptation shifts toward maintaining function under compromised conditions, embedding instability into the system. The direction of adaptation, therefore, depends on the quality of available inputs rather than on the presence of adaptation itself. Oxidative and chemical exposure introduce structural disruption that must be countered through repair and replacement. Reactive species alter lipid geometry and damage proteins embedded within membranes. In response, cells increase turnover and activate repair pathways to restore function. If the rate of damage exceeds the capacity for repair, membranes accumulate defects that alter permeability and signaling behavior. Adaptation in this context becomes a trade-off, where the system maintains function at the cost of increased variability and reduced efficiency. Mechanical stress affects membranes through shear forces, pressure changes, and repeated deformation. Endothelial cells in blood vessels, for example, experience constant fluid shear that influences membrane organization and receptor distribution. Adaptation to these forces involves reinforcing structural elements and adjusting lipid composition to resist deformation while preserving flexibility. This ensures that transport and signaling remain controlled even under continuous physical stress. Light exposure and circadian input influence membrane-associated processes through timing mechanisms. Hormonal signals that follow daily cycles adjust metabolic activity, repair processes, and energy production. Membranes must respond to these signals within defined temporal windows. Stable membrane conditions allow these rhythms to be expressed consistently, while variability disrupts timing and creates misalignment between systems. Toxic compounds and xenobiotics introduce additional pressure by interacting with membrane components and altering their behavior. Some compounds insert into lipid bilayers, disrupting packing and increasing permeability. Others generate reactive species that accelerate damage. Adaptation involves both exclusion and repair, limiting the impact of these compounds while restoring structure where disruption occurs. The effectiveness of this response depends on membrane integrity and the availability of resources for repair. Energy demand fluctuates with activity and stress, requiring membranes to support variable levels of metabolic throughput. Mitochondrial membranes must adjust electron transport rates without losing gradient containment, allowing ADP production to scale with demand. Stable structure enables this flexibility, while compromised membranes leak energy and reduce efficiency under increased load. Adaptation, therefore, reflects the ability of membranes to adjust composition and behavior while maintaining core structural properties. These adjustments occur continuously through remodeling cycles that incorporate available substrates and respond to environmental signals. When inputs support stability, adaptation strengthens the system's ability to handle variation. When they do not, adaptation shifts toward maintaining function under degraded conditions, embedding instability into structure. Environmental pressures do not determine outcomes directly. They define the conditions under which structure must operate. The response of the system depends on whether membranes can adjust while preserving controlled permeability, signaling precision and energy efficiency. When these properties are maintained, the body adapts without losing coordination. When they are not, adaptation becomes a process of compensation that gradually shifts the system away from stability. Maintaining membrane quality under stress. Stress increases the rate at which membranes are challenged and degraded. Elevated temperature, mechanical strain, high metabolic throughput, and reactive species all act on the lipid bilayer, altering packing and increasing permeability. Maintaining membrane quality under these conditions depends on whether the system can limit structural disruption while sustaining the processes that repair and replace damaged components. The outcome is determined by the balance between damage introduction and repair capacity, with membrane composition acting as the primary variable that shifts this balance. Structural resistance begins with lipid selection. Saturated and monounsaturated fatty acids maintain tighter packing and resist deformation when exposed to thermal or mechanical stress. This reduces the likelihood that membranes will transition into states of excessive fluidity or permeability. Cholesterol reinforces this effect by occupying space between phospholipids, restricting movement under heat while preventing rigid collapse under cooling. When these components dominate, the membrane maintains a consistent barrier even as external conditions fluctuate. Oxidative stress introduces direct chemical modification of lipids. Reactive species target double bonds, altering molecular geometry and disrupting bilayer organization. This creates defects that increase leakage and interfere with embedded protein function. Membrane quality is preserved when the rate of oxidative damage is limited and when damaged lipids are rapidly identified and removed. Antioxidant systems reduce the frequency of these modifications, while enzymatic repair pathways extract altered lipids and replace them through remodeling cycles. The effectiveness of this process depends on both the availability of stable replacement substrates and the energy required to drive repair. Turnover rate increases under stress as more lipids require replacement. This raises the demand for transport and remodeling, placing additional load on metabolic systems. If substrate delivery remains consistent and energy supply is sufficient, accelerated turnover can restore membrane integrity without introducing variability. If either is limited, partial repair leads to accumulation of mixed lipid populations, reducing uniformity and increasing susceptibility to further damage. Protein function within membranes must also be preserved. Receptors, transporters, and channels depend on specific lipid environments to maintain their conformation and activity. Stress-induced changes in membrane composition alter these environments, affecting how proteins behave. Maintaining lipid consistency ensures that these proteins continue to operate within defined parameters, preventing shifts in signaling or transport behavior. Mitochondrial membranes require particular stability under stress due to increased energy demand. Higher throughput in the electron transport chain elevates the potential for electron leakage and reactive species generation. Cardiolipin composition and membrane packing determine how well the inner membrane contains these processes. When integrity is preserved, ADP production scales without excessive loss. When it is not, energy efficiency declines and oxidative damage increases, reinforcing structural degradation. Transport systems must continue to regulate substrate and ion movement despite increased stress. Controlled permeability ensures that gradients remain intact, allowing cells to maintain internal conditions even when external pressures fluctuate. Disruption of this control leads to imbalance in ion concentrations and substrate availability, further impairing function. Temporal control of signaling and repair processes becomes more critical under stress. Activation of protective responses must occur quickly, but termination must also be precise to prevent prolonged disruption. Stable membrane conditions allow these processes to operate within defined time frames, avoiding overlap or persistence that would increase system strain. Maintaining membrane quality under stress, therefore, requires a coordinated response that limits damage, supports rapid and accurate repair, and preserves the structural environment required for protein function and energy production. By controlling lipid composition, sustaining energy supply, and reducing oxidative burden, the system can operate under increased demand without allowing structural degradation to accumulate. This preserves the integrity of membranes across tissues, ensuring that stress does not translate into long-term instability. Preventing regression. Structural stability is not permanent once achieved. Membranes remain in a constant state of turnover, and without continued control over inputs and conditions, they drift back toward the same patterns that produced instability. Regression is not a sudden failure. It is a gradual shift in membrane composition, signaling behavior, and transport properties driven by small changes that accumulate over repeated remodeling cycles. Preventing this drift requires maintaining the conditions that originally established stability so that each cycle of replacement reinforces structure instead of eroding it. The primary control point is the substrate pool. Every remodeling event draws from the available fatty acids and lipid components present in circulation and storage. If this pool shifts toward unstable or oxidized lipids, those materials are incorporated into membranes during normal turnover. The change is incremental but persistent, altering packing density, increasing susceptibility to damage, and disrupting receptor environments. Maintaining a stable substrate pool ensures that replacement cycles continue to produce membranes with consistent mechanical and electrical properties. Oxidative pressure must remain within the system's capacity to repair. Even with stable substrates, excessive reactive species accelerate damage and increase turnover demands. When the rate of damage rises above repair capacity, incomplete replacement leads to accumulation of defects. Preventing regression, therefore, involves limiting conditions that elevate oxidative load so that repair systems can operate without deficit. Energy availability underpins all maintenance processes. Remodeling, transport, and repair require ADP, and any reduction in energy production constrains these functions. When mitochondrial efficiency declines, maintenance becomes inconsistent, allowing degraded structures to persist. Sustaining energy production supports continuous replacement and prevents gaps in maintenance that would otherwise permit regression. Transport systems must continue to distribute lipids and associated components evenly across tissues. Disruption in transport leads to localized regression, where some areas maintain structure while others degrade. Uniform delivery of substrates allows maintenance processes to proceed consistently, preserving alignment between tissues. Signaling environments must remain stable to coordinate maintenance across the system. Hormonal and neural inputs regulate the rate of remodeling and repair, adjusting these processes to match conditions. When signals are interpreted consistently, maintenance remains synchronized. Variability in signaling leads to uneven rates of replacement, creating structural divergence that can expand over time. Exposure patterns determine the long-term direction of remodeling. Short-term deviations have limited impact, but repeated or sustained exposure to destabilizing inputs shifts the equilibrium of membrane composition. Preventing regression requires maintaining conditions that favor stability over extended periods so that cumulative effects continue to move the system toward consistent structure. Feedback mechanisms help maintain stability when outputs accurately reflect internal state. As membranes remain consistent, feedback loops regulate processes without overcorrection, preserving balance. If regression begins, distorted outputs disrupt feedback, allowing further drift. Maintaining accurate signaling supports these regulatory systems in preventing deviation. Time remains the governing factor. Structural stability is preserved through repeated cycles that replace any emerging inconsistencies with stable components. When conditions remain controlled, each cycle reinforces the desired state, reducing the likelihood of drift. If conditions change, the same cycles begin to move the system in the opposite direction. Preventing regression, therefore, depends on sustaining the inputs and conditions that maintain membrane integrity. By controlling substrate quality, limiting oxidative disruption, ensuring energy availability, and preserving coordinated signaling, the system continues to rebuild itself in a stable configuration. Without these controls, continuous turnover becomes the mechanism through which instability reemerges, gradually shifting the architecture away from the state required for consistent function.